Okay, so I posted notes on static loading of springs. This is going to be fatigue loading of springs. So fatigue loading is when you have the spring goes through cycles of high, low stress, and understanding failure is important because sometimes springs are used for such applications where there's fatigue loading. So before we get into the design, let us talk a little bit about how we make the springs ready for fatigue loading. There's something called short peening. This is a process of, it's basically a process to increase the strength, so increase the fatigue strength. And I'll tell you what is done. So the way springs are created it's basically a strand of wire, and that wire is then wound as a spring. But before you wind it up, what you do is you basically shoot basically shots of size 1/64 of an inch onto the wire at high speeds. So 1/64 are sprayed at high speeds. On the spring wire. And the act of doing that actually increases the strength of the spring by 20%. So increases fatigue strength by approximately 20%. Okay, so that is what is short peening. Now let's get to the part of spring for fatigue loading, springs for fatigue loading. Now what we've seen before is that there is the SN curve, which tells you that for 10 raised to 3 and less than 10 raised to negative 10 raised to 3 cycles or 1,000 cycles, it's high cycle fatigue and low cycle fatigue. And then there is a period from 10 raised to 3 to 10 raised to 6, a million, which is considered finite life, and then there's infinite life. The way you design springs is basically you never really hit the finite life. You always design them for infinite life. So we really don't need to look at the entire SN curve. Right? SN curve was something like this. So this is the finite life, and this is the infinite life. Infinite life. And so we always design springs in this region. Springs. So springs are always designed for infinite life. Springs. This region. So infinite life. A lot of work has been done by a guy called Zimmerly. And so in his, I guess in his honor, they call it a Zimmerly endurance strength. And I'll get to what Zimmerly did in just a bit. Okay, so what Zimmerly found was that the size, the material, and tensile strength have no effect on the endurance of springs, provided the size of the springs is 3/8 of an inch or less, or 10 mm or less. So Zimmerly found that size, material, tensile strength have no effect on the endurance for springs of size 3/8 of an inch, which is also about 10 millimeters. Okay, so that's basically his contribution. And he also went ahead and did this, what we've always done in this course is, yeah, question.
3/8, do you mean length of the spring or the diameter?
The diameter of the spring. Okay, so this course has always been on doing the empirical tests, sort of creating formulas and plots, and then using those plots tables to design things. So what he did was the following. So this is what he did. So he took springs. He took both types of springs, unpeened as well as peened. And always peened ones are stronger because they have those shots plastered on them. And then what he did was he basically subject the springs to cyclic load. So this is the function of time. This is going to be sigma max, sigma min, and units of k psi. And he actually used a very specific values for these. So for unpeened, he used sigma min equals 20 k psi and sigma max of 90 k psi. For peened, he used sigma min of 20 k psi and sigma max of 135 k psi. Okay, so he did this tests on many different springs of many different materials, and he found that that springs don't fail for cycles beyond 10 raised to 6, which is our definition for infinite life. So they have an infinite life. So with this empirical data, now we will go ahead and try to come up with criteria for designing springs. Okay, so let's proceed. So what we'll do is, using this empirical data, we will compute the strength. So we'll compute the endurance strength. Okay, normally we use, what did we use before? We used tau A, tau M, but we'll just use this. We'll use S for this. So SSM is sigma max minus sigma min divided by, sorry, plus, right? And SSA, the average, so the SSM is average and SSA is the amplitude. Sigma max minus sigma min divided by 2. Okay, so using this formula, what we can do is we can compute the values for SSA for unpeened ones. So all you have to do is you need to substitute these values. So we have these values, 20 and 90, in this formula for sigma max, sigma min, and then we have SSA and SSM for unpeened and peened. So SSA comes out to be, so example would be just to 90 plus, so 90 minus 20 divided by 2, that is 35 k psi. SSM is 90 plus 20 divided by 2, that's 55 k psi. Similarly for peened, SSA, and I won't do this here, you can check it, 57.5 k psi. We use a max of 135, min of 20, and then SSM equals 77.5 k psi. You could also have this in MPa. I'll just put it down. MPa. In case your problem is in SI units, this is what you'll use. $398 MPa, 534 MPa. Okay, so we're getting to the design, but this is what we get. This is now going back to the mean and average stress, which we had used for the Goodman and Gerber criteria, right? So we're getting there through this. So we have computed this. Now let's go and design part, which is there are two. Well, there's the criteria which people normally use for springs is the Goodman criteria. So these can be used with the Goodman criteria. The only reason why I use it with the Goodman criteria is because the Goodman criteria actually is a predictor of stresses in a spring, and not all of them are actually useful for springs. Like the Soderberg asymmetry elliptic are not going to be useful. It's the Goodman and Gerber which are going to be used because they actually tell us something about the failure. Again, that's an empirical thing. It's not something which we can guess unless we do experiments. So the Goodman equation, if you remember, it was sigma A divided by SE, the endurance strength, sigma M, the mean stress, divided by ultimate strength equals 1. So we can modify this for a spring. What we do here is we replace sigma A with SSA, we replace SE with SSE, sigma M with SSM, SUT with SSU equals 1. Okay. Now there's an empirical formula which is SSU. The ultimate strength of a spring is 0.67 SUT. This is again an empirical thing. This was probably covered in chapter 6, where this chapter on shafts, we had this formula. So it's something which we know again from experiments. Okay, so what I'm going to try to do now is try to compute the value for SSE. Why we need SSE is because SSE is the endurance strength, right? Knowing SSE, once we know SSE, we can design the spring because that tells you the maximum stress we are allowed to use a spring under fatigue loading. So we need to compute SSE. That's going to be our goal. Okay, so this is how we do it. To give you a better picture, maybe we'll draw the Goodman equation. So now we need to plot the Goodman equations for on this curve, SSA on the y-axis, SSM, just exactly like what we had before, sigma M, sigma A, but here it's replaced with S. We know the Goodman curve passes through SSE and SSU. So this is our Goodman curve. Now we know that from the tests which Zimmerly did, 1 point on this curve is SSA and, 1 point on this curve is SSA and SSM, right? So 1 point is, we saw that SSM for, if you go here, for unpeened, the SSA is 35 kps and 55 kps. So that is 1 point which lies on this curve. And so we can use that to our advantage to compute SSE as you see it just in a bit. So we know that SSM is 55 and SSA is 35, and that's 1 point. Okay, so we know that point passes, this curve passes through those points. So what we'll do is we'll take this equation and substitute the value of SSA and SSM. So SSA is 35, SSE is unknown, SSM is 55. Now SSU is 0.67 SUT. I'm just going to assume some value for SUT. So SSU is 0.67. So one of the springs, and if I think I forget the exact spring material, but this is from one of the tables, might be, is it here? So there are a couple of springs, and for each spring you can compute SUT, right? You can compute SUT from this formula. So let's say that we've already computed SUT, that SUT is, I'm going to put the SUT in here. So let's say that SUT I have is 315.67. That is 211.5 kpsi. Okay. Now I'll put this value here, 211.5 equals 1. So let's move it down. Okay. Solve for SSE. We get SSE is 47.5 kpsi. Okay, so this is very useful because now with this value, we can go ahead and design a spring. We need to ensure that the SSE, this is the endurance strength, is 47.5 kpsi and below that. So that's one criteria, the Goodman criteria. Another criteria which is normally used is the Gerber criteria. And we can do the same thing for the Gerber criteria. Okay. Another common criteria is the Gerber criteria. Okay, so for Gerber criteria, the equations are slightly more involved. It is SSA divided by SSE plus SSM divided by SSU square equals 1. If you want to see how that looks like, if you do a similar plot, SSM, SSA, so it passes through SSU and SSE, and the curve looks, it's basically a parabolic curve. It looks like this. Okay, and what you know from this figure is that I should be like this. Okay, what we know is that one point on this curve is SSM, which is equal to 55. Another point is SSA, which is 35. The same criteria as we've seen before. So what we can do is we can substitute this. Again, the goal here is to compute what SSE is based on this criteria. So SSA is 35, SSE is unknown, SSM is 55, SSU, we computed that earlier, it is 211.5 kpsi square equals 1. So we can easily solve for SSE. It is 37.5 kpsi. Okay, so this is just giving you another value for SSE. So we can see that SSE is 37.5, but using Goodman criteria, SSE is 47.5. So you can see that Gerber is more conservative. It's predicting that failure will occur at a lower threshold, 37.5, versus Goodman, which tells you at 47.5. So this was Gerber. Then we looked at Goodman, and there's one more criteria, which is a new one, and go through that before we solve a problem. So that's the Gerber criterion. There's a third criterion, which is called the sign criterion. Sign criteria for endurance strength. Okay, now there are some conditions under which this applies. It only applies for a certain finish. So it's applicable for polished, notch-free, cylindrical, springs. So the surface, well, the wires should be cylindrical, polished and notch-free. What this says is that SSA is constant. Okay, unlike the Zimmerly, which said that SSA is variable, SSA is basically constant and independent of SSM. So we do not need to use SSM in designing this, provided SSM is not greater than SSU. Okay, and so important is does not hold for specimen with notches and abrupt change in section.
The second bullet point, the last word, is that SSA or SSU?
SSU. Okay, so I'm going to basically summarize what we have done so far and get to a problem. Okay, so we have looked at 3 criteria, and this is basically all the formulas we need for fatigue calculation. So let's go through them one by one. So this is something which we've seen before. The ultimate strength of springs depends on the diameter. A and M are available in table A10.4. This is something which I have in the previous class notes, but this is basically a table which, given the material, given the ASTM number, you can compute M and A. And once you have M and A, and you should just use the diameter to compute the ultimate strength. So that's one. The second thing is SSU is always 0.67 SUT. This is from the shafts chapter. FA and FM are basically the average forces and mean forces. Amplitude of the force FA and mean forces FM. So that comes from F max, F min. Tau A is the average shear stress, and tau M is the is the amplitude of the shear stress, and tau M is the average shear stress that can be computed. KB is a factor, a stress concentration factor and curvature factor. D is the nominal diameter of the spring, while D is the, so if you have a spring, this, That's going to be capital D, and then the coil diameter is going to be small d. Okay, so then we have the Goodman criteria, which I just wrote down. You can also compute the factor of safety by just replacing SSA with SSA divided by N, where NF is the factor of safety. This is the Gerber criteria. You can compute the factor of safety from the same thing by doing SSA divided by M, NF, and SSM divided by NF. And then the sign criteria is only true for certain types of specimen, notch-free, cylindrical, right, and polished. And so you know that SSM doesn't, the mean stress doesn't affect the factor of safety. So this is how you compute the factor of safety just using SSA and tau A. Okay, so with that, let's solve a problem. Okay, here is the problem. So helical compression spring made of music wire has a wire size of 0.0198 inch. Okay. So what that is wire size means the diameter, the small d, 1092. So again, as I said, if you have a spring like this, keeps going on, this diameter is small d, and then the average diameter is capital D, and then the outside diameter is DO. So what you're given here is small d, outside diameter, you're given DO, which is 9/16 of an inch. And usually the calculations involve capital D. So we know that just from this figure, you can see that D0 is the diameter, nominal diameter plus D. And so it's easy to compute D. It is DO minus D. So that comes out to be 0.092 minus, sorry, 9/16 minus 0.092, which is 0.4705 inch. Okay, free length of 4/3 of an inch. Don't think we need the free length. Okay, the spring is unpeened, so this is kind of critical. That will determine the kind of Zimmerly data you'll use, because they have different values for SSA and SSM. The spring is assembled with a preload of 5 lbf and will operate with a maximum load of 35 lbf. This just indicates that F min is 5 lbf, F max is 35 lbf. Okay, so given all this, we need to estimate a few things, factor of safety in particular. So the factor of safety, assuming Gerber failure and Zimmerly data, factor of safety using Science torsional formula, and factor of safety assuming Goodman failure and Zimmerly data. Yeah, so it's just straightforward application of everything we've done so far. So let's go with each of these. Okay, so first, this is just going to be application of the formulas I have over here. So what do we need for, see, what do we need for Gerber? We have this formula, right? Factor of safety is unknown. We need SSE, SSU, sorry, Gerber is here, my bad. SSU, let me just copy this down, and then we can just go reverse engineer and figure out what we need. So SSU, tau A, tau M, let me just write it down. So we need tau A, tau M, SSU, SSE, what else? Yeah, that's it. All these Once you have this, the second part is kind of straightforward. Okay, so let's see how to compute tau A and tau M. I think we have the formula here. Tau A is KB 8FA D divided by pi D cube, and tau M is that. So let's compute that. Tau A is KB 8FA capital D pi D cube, and tau M is KB 8FM capital D divided by pi small d cube. So KB, okay, this is something which I don't have in the formula sheet, but I put it in the previous lecture notes. KB is see, the formula is 4C plus 2 divided by 4C minus 3. Okay, so C is capital D divided by small d. So capital D is 0.4705, small d is 0.092, so this is 5.11. With that, we can compute KB. So KB comes out to be 1.287. It's non-dimensional. So let's see, we've knocked down KB. We know what capital D is. We know what small d is. We just need FM and FA. Okay, FA is, and if you go back, FA is basically the amplitude. So it's F max minus F min divided by 2. And I believe we know what F max and F min is. So F max, well, F min is 5, F max is 35. So let's use that. FA is F max minus F min divided by 2. F max is 35. F min is 5. So it comes out to be 20 lbf. Is 15. Okay. F max plus F min divided by 2 is 35 plus 5 divided by 2. Is that wrong? 35 minus 5 is 30. It should be 15. This should be 20. Okay, so I think we are all set. We've computed FA, FM. Now all that remains is tau A and tau M. So jumping here, we have tau A is KB 1.287 times 8 times FA 15. Capital D is 0.4705 divided by pi. Small d is 0.098092 cube. And then tau M is 1.287, 8 times 20 times 0.55 divided by pi, 0.092 cube. Okay, it's a bit of calculations here, but this comes out to be, so tau A, I get 29.7 kpsi, and tau M is 39.6 kpsi. Okay, so why were we even computing tau A and tau M? Well, because the Gerber criterion requires us to compute tau A and tau M. That's why we did all this calculation. What else did we need for Gerber? Well, we made a list. So now we have got these values. We need to compute these values. What's SSE? SSU. So SSU, go back to the formulas. SSU here is 0.67 SUT. But we need to compute SUT. So how do we get SUT? Well, SUT comes from table 10.4. Okay, so table 10.4 is here. For SUT, we need to know the type of wire and we need to know the diameter. So let's see what if you are provided information about that. Okay, it says music wire. Okay, and then we also need to know the coil diameter. We need to know D, right? D is 0.092. So we go to table 10.4. We look at music wire. The exponent is 0.145 and A is 201. And then it also needs D. D is 0.092, right? So we, from table 10.4, for music wire, we have A equals 201, M equals 0.145, and we know that D for this particular spring is 0.092. Okay, so here we are SUT. So from all these, we can compute SUT is A divided by D raised to M. A is 201, D is 0.092, M is 0.145. So SUT is 284.1 kpsi. And we know that SSU, so there's a formula here in the sheet, SSU is 0.67 SUT. So 0.67 of 284.1 comes out to be 190.3 kpsi. Okay, so we've knocked down SSU. So again, go to our list of things we need to compute. We have now nailed down SSU. We need to nail down SSE, and then I think we should be good. Now, SSE is very specific to the criteria we are going to consider. Gerber would have a different SSE. Goodman will have a different SSE. How do you get that? Well, if you remember, if you go back here, remember we were computing SSE. If you knew SSU, SSM, SSA, SSA and SSM came from Zimmerly data. SSU is something which we have computed for music wire. So we can compute SSE using the same kind of equations. So that's something we've done. Let me just repeat this for this particular problem. So now is the time we sort of specialize and solve for each of these individual criteria. So let's go with Gerber. For Gerber, we know the equation is SSA divided by SSE plus SSM divided by SSU square equals 1. And we know from Zimmerly data that SSA is, so what is it, peened or unpeened? We have to go back and check. That is, I think it's unpeened. Yeah, it's unpeened. So for unpeened, we saw that the values for Zimmerly data are right here. Yeah, unpeened is 20 and 90. No, sorry. SSA and SSM here. Unpeened is 35 and 55. So we need to use 35 and 55. Now, if the question said peen, then you need to use these values. Okay, so don't just blindly use 35 and 55. They just depend on the situation. This is for unpeened, this is for peen. They're different values. If you get a wrong answer. So 35 and 55 is what we need to use. SSA is 35. SSM is 55. Substituting this formula, well, and SSU is, we just got it, it's 190.3. So here we are. So we have SSA. I'm just going to substitute in the formula. 35 divided by SSE plus 55 divided by SSU. Well, SSU is 190.3. Square equals 1. From that, we can compute SSE to be 38.2 kpsi. So that's step 1. Now that we have SSE, so here we have computed SSE, and that basically gives us everything we need. So the formula we need to use is right here. Let's copy this. Copy. So SSU is 190.3. Tau m, this is something which we had just computed. Tau m is 39.6 and tau is 29.7. 39.6, tau is 29.7. SSE, we just computed that, 38.2 minus 1 plus 2 times tau m, which is 39.6. SSE is 38.6. Tau A is 29.7. And then finally, SSU is 190.3. The whole thing squared, a bit messy. But putting all the numbers together, you get 1.23. Okay, so that's the answer. Okay. Okay, 2 more parts, and we're done. Part B is we need to compute factor of assuming signs torsional failure. For signs torsional failure, it's actually kind of easy. If you know SSA and if you know tau A, then you can compute NF. But we know what SSA is, right? From Zimmerly data, we know that SSA. So from the Zimmerly data, yeah, SSA is 35, and tau A is something we've computed. It is 29.7. So we can easily do part B. $35 divided by 29.7. So this gives NF is 1.18. Okay, and the last step, the last question is do the same with Goodman. So for Goodman, if you look at the formula for factor of safety, which is here, what you need is tau A, tau m, which you already have computed. SSU we've computed. The only thing we need to compute is SSE. So how you compute that is again using this formula. So let's compute SSE, and then it should be very easy to compute NF. Okay, so the formula for Goodman is SSA divided by SSE plus SSM by SSU equals 1. from Zimmerly data, SSA is 35. SSE is unknown. SSM is 55. SSU is 190.3. Go to 1. This gives me SSE equals 49.23 kpsi. So one step, we're very close. The formula from here is NF is, just copy this. Copy. Okay, so let's substitute NF equals tau A. Again, tau A is something we've computed. It is 29.7. SSE, we've got here 49.23. Tau M we've computed before, it's 39.6. SSU is the same for, it's a material property. We've computed that, I believe here. SSU 190.3. Is to -1. So NF is 1.23. Okay. Okay.